condenser keeps your food cold without making ice inside it. It's all about moving heat, not creating cold. There are five major components of a refrigerator. First is the refrigerant, the compressor, the condenser coils and expansion device, and evaporator coils. The refrigerant is a special fluid that easily changes between liquid and gas at low temperatures. It's the carrier of heat. It follows the first law that energy is conserved. The refrigerant absorbs heat in one place and releases it in another. So energy doesn't disappear, it just moves with the fluid. The compressor is basically the heart and the work input of the system. It takes low pressure, low temperature refrigerant gas and compresses it into high pressure, high temperature gas. This is the second law in action. Heat naturally flows hot to cold, so to make it flow cold to hot, you have to put work into the system. The compressor provides that work using electricity. Without it, heat wouldn't move from your cold fridge to the warm kitchen. The third component is the condenser coils. These are the hot coils usually at the back or bottom of the fridge. The high pressure hot gas releases heat here and condenses into a liquid. The first law again is in action. The heat removed from inside the fridge plus the work from the compressor gets dumped out through these coils. That's why the back of the fridge feels warm because energy is conserved. Next is the expansion device. After the condenser, the liquid refrigerant passes through an expansion valve or capillary tube. Pressure drops suddenly and the refrigerant becomes a cold, low-pressure liquid vapor mix. This is an irreversible expansion because the temperature drops without removing heat yet. It prepares the refrigerant to absorb heat again. The zeroth law shows up here too, where heat will flow from the warmer fridge interior into the colder refrigerant when they touch. The last one is the evaporator coils. So these coils are inside the fridge. The cold refrigerant absorbs heat from your food and air, evaporates it into a gas, and cools the interior. This is heat transfer driven by this zeroth law, where heat flows spontaneously from the warmer fridge interior to the colder refrigerant until they reach thermal equilibrium. The refrigerant then goes back to the compressor and the cycle repeats. So basically, a refrigerator doesn't make cold, it uses work from the compressor to move heat from a cold space to a hot space. So now we have the air conditioning. So the air conditioning also has these important components and uses these three laws of physics that makes this possible to work. An air conditioner cools your room by moving heat outside. It doesn't create cold. It uses 8 main components working in a loop. So first we have the refrigerant, or also called the freon, which is a special liquid that works. It's designed to boil and condense at low temperatures so it can carry heat easily. This is the first law where energy is conserved and the refrigerant absorbs heat inside and releases it outside where nothing is lost, it just gets moved. Next we have the compressor. Here we have the compressor. The compressor squeezes the low-pressure refrigerant gas into high pressure and high temperature gas. It's powered by electricity. So this is the second law, where heat doesn't flow from cold to hot on its own, and the compressor does work to force heat to flow uphill from your room to the outside. Now we have the outdoor unit and condenser fan here. The outdoor unit houses the condenser coil and the condenser fan. The hot refrigerant flows through the coil, and the fan blows outside air over it to carry the heat away. The refrigerant condenses into a liquid here. So the first law again, where the heat from your room plus the work from the compressor equals heat dumped outside. That's why the outdoor unit blows hot air, and this is where the energy is balanced. Next, we have the expansion valve. This is the liquid refrigerant. The liquid refrigerant passes through the expansion valve, and its pressure drops suddenly, and the refrigerant gets very cold. This prepares the system for heat absorption, where the zeroth law matters here, because heat will flow from warmer to colder objects when they touch, and we've just made the refrigerant colder than your room. Next, we have the interior unit and evaporator. The evaporator has two parts, the pipes and heat sinks. The interior unit contains the evaporator, and it's made of pipes and heat sinks, also called fins, to increase surface area. The cold refrigerant absorbs heat from the room air passing over it and evaporates into a gas. Zeroth law is in action, where heat flows spontaneously from the warmer room air to the colder refrigerant until they reach thermal equilibrium. That's how the air gets cooled. Cool. Now we have the PCB and the switch. The PCB, or printed circuit board, here is the brain. It reads the thermostat and controls the compressor, fan, and valve. The switch turns the system on and off. Thermodynamics at work here is the PCB maintains the system near equilibrium at your set temperature. When the room reaches the set temperature, it cuts power to stop the cycle. No energy is wasted once equilibrium is reached. So, generally, the full cycle is evaporator absorbs heat from your room, the compressor adds work to raise the refrigerant's temperature and pressure, the condenser releases that heat outside, and the expansion valve drops the pressure to cool the refrigerant again. And now we have internal combustion engine for automobiles. So a car engine turns the chemical energy in fuel into motion. It does that with pistons, valves, and crankshaft running a four-stroke cycle, and every step is governed by the laws of thermodynamics. The four important strokes mentioned is the intake, compression, power, and exhaust. Intake stroke is when the piston moves down. The intake valve opens, and the air-fuel mixture gets sucked into the cylinder. This starts the cycle at low temperature and pressure, and the zeroth law sets the stage. Temperature differences exist, so heat transfer can happen later. Next is the compression stroke. So both valves close, the piston moves up and compresses the mixture. This raises its temperature and pressure, and the first law of thermodynamics works here, where work is done on the gas. You're putting mechanical energy into the mixture, raising its internal energy, and this is why the mixture is ready to burn. Now we have the power stroke. The spark plug ignites the mixture. The combustion releases a huge amount of heat, creating high pressure that forces the piston down. This is the only stroke that produces work. First law, where chemical energy and fuel converts to thermal energy, then to mechanical work pushing the piston. Then the second law, where not all heat becomes work. Some must be rejected and waste heat. That's why engines are only 25 to 35% efficient, and heat naturally flows hot to cold, so you can't capture it all. Next, the last one is the exhaust. The exhaust stroke, where is a process by which the exhaust valve opens. And the piston moves up and pushes burnt gases out. In thermodynamics, waste heat leaves the system through the exhaust, and the second law forces this. A heat engine needs a hot source and a cold sink. The atmosphere is the cold sink. So, basically, the engine is a heat engine running the Otto cycle. The intake, compress, burn, expand, and exhaust. You put chemical energy in, get mechanical work out, and dump the rest as heat. The second law guarantees you'll never get 100% efficiency. That's why cars have radiators, cooling fans, and exhaust systems to manage the waste heat the second law demands. So that is all.